So we'll just jump into the do now, and then I'll talk about what we're going to go through today and for tonight into tomorrow. So for number one, if a buffer is made of NH3 and NH4Cl, which component of the buffer will neutralize a small amount of HCl that is added? So I put this buffer in the do now because this is a little bit different. We have NH3, which is ammonia. So part of the base is NH3, part of the base is NH4+. Cl is commonly a spectator ion. Not always, but commonly. So that's why on the board I kind of have a dotted line with Cl-. So we have NH3 and NH4+. We have to first figure out in this buffer which is the acidic component and which is the basic component. Because in a buffer, you always need a weak acid and a weak base. So when you look at this, just remember that the acid always has one additional H+. Because when you're thinking about a conjugate acid-base pair, the conjugate acid is what is produced after the base accepts the H+. So if you're comparing NH3 and NH4+, right, NH4+ has the extra H. So this is actually the weak acid portion of the buffer. Ammonia, NH3, is a weak base. So we've talked before about how ammonia, so again, this is ammonia, is a very common weak base. Very common weak base. So it's good to know that NH3 is ammonia, that's a weak base. NH4+ is its conjugate acid. To get NH4+, it has to come in the form of a salt, which is why we see the Cl-, but it's a spectator, so we can just ignore it. So now that we've labeled the different parts of the buffer, it's asking which component will neutralize a small amount of HCl. So HCl is a strong acid. Neutralize means you have an acid plus a base. It creates a salt and water. So if we're adding an acid, the part of the buffer that will neutralize a small amount of that acid is the basic part of the buffer. So that would be NH3. So the basic component of the buffer, the weak base, will react with the acid to neutralize. And number two, write the complete ionic and net ionic reaction that occurs when HCl is added to the buffer above. So complete ionic means we show everything, all ions. Net ionic, we're going to cancel out spectators. So we already said that NH3 is going to react with the added HCl. NH3 is a weak base, so it stays together as a molecule. HCl is a strong acid. So like I showed yesterday, right here's HCl. You put this into water because it's strong, it immediately ionizes. So when we write H+, it's going to be plus, or sorry, when we write HCl, it's going to be plus H+ plus Cl-. Now think about what it means about a base. A base will accept a proton. So NH3 will accept an H+. It's going to become NH4+. Then we just have the Cl- left over. So again, the reason that NH3 did not break apart is because it's a weak base. If it were strong, it would break apart. So this is the complete ionic. Net ionic, we cancel spectators. Do we have any spectators here? Cl. All right, Cl- is the exact same on each side. So NH3 plus H+, gives NH4+. There's our net ionic. Bases look a little bit different than the acidic cationic that we looked at yesterday. But just remember, bases always accept a proton. This is a very common basic buffer. They gave us all of the information. We could calculate the pH. We would find that it's actually going to probably be above 7. Because it would be a basic buffer. It's a base, and it's conjugate acid. Any questions on the do now? We'll work more with this as we continue to go throughout this chapter. So if there aren't any other questions, I'm just going to briefly talk about what today will look like. You can get out your notes while I'm going through and talking about this, because we will be starting with example 8 from the notes. So we did not get to example 8 yesterday, so we will start by going through that example. It's actually a practice free response question related to buffers. So it'll give you some practice with the AP style free response. So we'll start with example 8. Then we'll look at the answers to the buffer practice questions that I posted on Google Classroom yesterday. We'll go over the answers, answer any questions. These are very similar to quiz questions that you might see. Looking at what's the best buffer, what's the pH of a buffer, things like that. Once we go over the answers, I will post the answers to that Google Classroom post as well. So you can go back and refer to them if needed. And then we're going to look at the buffers practice from the practice packet. So remember, you have 2 packets. You have the notes packet and you have that practice packet that I had you guys pick up last week. I said we need it eventually. I just wanted you to have it. So we're going to actually do practice with buffers from that. Additional practice just to get you in the habit of what to look for with buffers, how to look at the calculations, net ionic equations, things like that. If for some reason we don't get it done during class, I'll just have you finish a couple questions tonight. More than likely, we're going to get it done, especially because we have a little bit of extra time. Quick note for tomorrow. So I won't be at school tomorrow. Tried to get stuff scheduled for the afternoon. Apparently, everyone tries to get appointments for the afternoon. So I won't be at school tomorrow. But if you actually notice on the board, rather than having you watch a little bit longer of a video tonight, I'm just going to give you time tomorrow during class to watch the videos on titrations. So 8.3 and 8.3b. So 8.3 is an overview of acid-base titrations. 8.3b is actually looking at the particle diagrams like we were looking at with buffers yesterday. I'm going to have you watch both of those during class. I know it's a 2-hour delay, but I'll still have you watch those. Whatever you don't get done in class, that's going to be considered the homework for tomorrow night. I will add reminders on the stream of Classroom tomorrow morning, just like a, hey, remember, this is what you need to do. You guys will not need to get on Google Meet. So if you want to make yourself a note, you don't have to get on Google Meet. You guys that are virtual, that are on Meet right now, you do not need to get on the Google Meet tomorrow. I mean, if you want to, great, but I'm not going to be on Google Meet. I'll just check attendance through Edpuzzle, right? If you're watching the video through Edpuzzle, I see that you were doing stuff during class. Gold group. So gold group, bring headphones to class. If you don't normally, bring headphones. And that's what you'll do tomorrow. So just watching a couple videos during class. And then Thursday, we'll jump into practice with titrations, look at examples, I'll answer questions, things like that. So that's just kind of a quick note for tomorrow, kind of gives you an overview. In terms of homework for tonight, because I'm doing this tomorrow, the only thing that's tonight is watching mastering, just working on mastering. So you just have extra time. You can work on mastering, you can work on the bonus. There's nothing for you to watch. You'll see that 8.3 probably pops up this morning. You do not need to watch it for tonight. It's just there so that I remember that it's there and I don't forget to put it on for you. But you can watch both of them during class tomorrow. So what we'll do is we'll just jump into example 8. So in your notes, if you flip toward page 17, probably. Back of 18. Okay, so example 8 is on page 18. This is actually a practice for response question. So what you're going to see is that it's not just calculate the pH of a buffer. This is actually two different parts that's going to scaffold and it's going to build. So we're going to take a look at example 8. I have it split on two different slides. I was working through this in my notes packet, and I had to kind of split underneath the question in half so that I had enough space to work through everything. For this example, it says a 1.2 molar NaOCl solution is prepared by dissolving solid sodium hypochlorite in distilled water. 98 Kelvin is prepared by dissolving solid sodium hypochlorite in distilled water at 298 Kelvin. 298 Kelvin is 25 degrees Celsius. The hydrolysis reaction, it gives us the hydrolysis reaction here. This hydrolysis reaction occurs. That's just something reacting with water, usually a weak acid or weak base. Part 1 says write the equilibrium constant expression for the hydrolysis reaction that occurs between OCl- and H2O. The equilibrium constant expression, that is a K expression. Now we can be more specific with what K it is, but let's just write the expression first. This hasn't changed for the last two chapters. Products over reactants. And look at the hydrolysis reaction that they give us up here. So HOCl times OH minus over OCl minus. Should I include water? No, it's a liquid. Okay, pour water always gets ignored. Now the K is based on what we see, right? What's being produced in here, that tells us what K expression it is. If you're producing hydroxide, that tells us that it's a base, Kb. If it produces H+, it's Ka. If it doesn't produce anything and it's just a general expression, it'd be Kc or Kp. Part 2, calculate the value of the equilibrium constant at 298 Kelvin for the hydrolysis reaction. So just keep in mind that 298 Kelvin is 25 degrees Celsius. Now I want to point out that they give you a table over here. They give you a table right here. Notice here they give you Ka values at 298. Oh, we look at it and we're like, okay, well, we want Kb. We want Kb of the conjugate base. We have Ka of the acid. We want Kb of the conjugate base. Well, remember, if you have a conjugate acid-base pair, Ka times Kb equals Kw. This is on the equation sheet. For any conjugate acid-base pair, Ka times Kb equals Kw. 298 Kelvin, 25 degrees Celsius, that means that we can use 1 times 10 to the negative 14th for Kw. So they gave us Ka in the table, 2.9 times 10 to the negative 8 times Kb, that's what I'm solving for, equals Kw, 1 times 10 to the negative 14. I'm going to use my marker over here just to remind us for any conjugate acid-base pair, Ka times Kb equals Kw. When we say conjugate acid-base pair, that could mean the acid and the conjugate base, or the base and the conjugate acid. Anything that differs by just one H+. So since this is HOCl, and we're looking at the reaction of OCl-, we're looking at the conjugate base. And then part 3, calculate the value of OH minus in the 1.2 molar NaOCl solution at 298 Kelvin. Okay, OH minus solution. I'm going to make something very, very small up here at the top. Right, technically, we need an ice table. So 1.2 molar NaOCl. Na plus is a spectator. That's how we get OCl minus. 1.2 molar. We ignore water. We have 0 and 0. Minus x plus x plus x. So this looks more like chapter 16. Which is all that this chapter is. It's just an extension of chapter 16. So here is our equilibrium amounts. Here's our equilibrium constant. So let's go ahead and just plug everything in. We already have our expression, so I'm not going to rewrite the expression because we have it up here already. So KB, 3.4 times 10 to the negative 7th is x times x over 1.2 minus x. Remember, if you make the assumption to write it down. So when I assume x is small, I can ignore that minus x. When I assume x is small, I can ignore that minus x. And when we solve for x, we get 6.4 times 10 to the negative 4th. Now the point of part 3 was to calculate the value of OH minus. Well, x is OH minus, so I'm just going to label this molar. I'm going to go ahead and just put equals concentration of OH minus. So again, this is all prior chapter. Looking at a base, how it reacts with water, using the idea that Ka times Kb equals Kw because it's a conjugate acid-base pair. And then we're solving for x. We assume x is small. That allows us to neglect x on the bottom. We get our value of OH minus. That's the first part of example 8. Now, I do want to just tell you, what if you get to part 2 and you're like, I don't know what K is. And you realize that for part 3, you need a value of K. You can make up a number. You could make up a number. You could use Ka. And if you use this number, whatever number you make up, in part 3, you still get the point for part 3. So it's not, if you miss one part, you miss it all. If you miss part 2, you would miss the point for part 2, but if you use that value in part 3 and you do it correctly, you get that point. So it's all conditional grading. So now we're going to take a look at the second part of example 8. I'm going to leave parts 1, 2, and 3 over here, and then I'll do the second part on the other half. So now it says a buffer solution is prepared. All right, so it's telling me that we have a buffer. It's telling me here that we have a buffer. I'm going to go ahead and just underline that. Buffer solution. That means I should have a weak acid and a weak base. It's prepared by dissolving some solid sodium hypochlorite in a solution of HOCl at 298 Kelvin. So here's my acid, hypochlorous acid. HOCl and HClO are actually the same thing. Here's the weak base. It's the conjugate base. pH of the buffer is 6.48. So they actually give us the pH of the buffer here. Part 1 says calculate the value of H3O plus in the buffer solution. So I'll say this is part B, part 1. Calculate the value of H3O plus. Remember, H3O plus and H plus are the same thing. You have pH. Think about how if you have pH, how can you go backwards to H plus? Well, remember, H plus is 10 to the negative pH. When we find the pH of the buffer, we take the negative log of H plus. Well, if they give us the pH, we can actually just do 10 to the negative 6.48. So second log is 10 to the x. The H plus concentration is 3.3 times 10 to the negative 7 molar. So that's just taking the value and going backwards. So see how this, again, pulling back in from before. It's talking about buffers, but it's using ideas that we looked at in previous chapters. Then part 2 says indicate which of HOCl or OCl minus is present at the higher concentration in the buffer solution. Support your answer with a calculation. So because it tells us to do a calculation, we need to do a calculation. Let's use the buffer equation. Because if it wants to know which one is at a higher concentration, we can look at the buffer equation and see which value would be greater. The buffer equation is H plus equals Ka times concentration of acid over concentration of base. So now let's plug in what we know. We just solved for H plus. They actually gave us Ka in the original part. So if you look up in that table, the Ka of HOCl, right, the acid, was 2.9 times 10 to the negative 8. And we're going to leave acid over base as a variable. So we're going to solve for acid over base as a variable. This is a very common way that they use math for a conceptual question. So if I do 3.3 e negative 7 divided by 2.9 e negative 8, if I divide this over, so we get 11.38 equals acid over base. Now you might look at this and you're like, okay. Let's think about what this is though. I'm going to make this look like the other side. 11.38 is the same as 11.38 over 1. Well, now it looks like the proportion on the other side. Acid to base is 11.38 to 1. So that means if I had 1 mole of base, I would have 11.38 moles of acid. So the acid is greater than the base. The acid is greater than the base. Because when I look at this ratio, the ratio of acid to base is 11.38 over 1. So the acid was HOCl compared to the base, which was OCl minus. So which is present at higher concentration? The acid. And then support our answer with a calculation. We did that here. Now another thing we could do is compare pH to pKa. So another way that we looked at yesterday was pH compared to pKa. Would they count this as a calculation? I wouldn't see why not. Because if you take the pKa of this, negative log of 2.9 e negative 8, if you take the pKa is 7.54. The pH is 6.48. Remember, yesterday we talked about if they're equal, we have equal amounts of the buffer. If the pH is less than the pKa, that means you have more acid. It's making the pH go down. So here, because pH is less than pKa, we would have more acid compared to base. So was this a buffer question like we looked at yesterday? No. But it's good to see different types of questions because this is a practice-free response question. So you can see really the only true new material from yesterday was part 2. Everything else was stuff that we had done before. Any questions on example 8 before we look at the practice from yesterday? No? All right, so then you can go ahead and you might want, if you want your notes for the practice that we're going to do in a little bit, you can keep them out. We are going to be looking at the practice problems and then the practice packet that you got last week. So what I did is I actually just put my answers, my work on the slides just to make it easy for everyone to see. I will go back and I'll add these to those practice slides, or I'll just make a slide deck that's called, practice answers. And you can go back and refer to these if needed. So question 1 was just calculate the pH of a buffer. You don't have to do any other calculations in terms of calculating the pH after something is added to a buffer. You just have to calculate the pH of a buffer. So they gave us the concentrations of each part. They gave us the Ka of the acid. So I labeled everything here, the weak acid, the conjugate base. And so the buffer equation is H plus equals Ka times the acid concentration over the base concentration. And we just do Ka times acid over base. That gives us H plus. We take the negative log of that to get the pH. All right, 3.89. If you went out to more decimal places or fewer, that's okay. Biggest thing is that you're showing your work throughout this process. The only equation we ever use for buffers is this equation, H plus equals Ka times acid over base. So practice question 1 was just finding the pH of a buffer. Practice question 2 was also finding the pH of a buffer, but this was a little bit different because this gave you a basic buffer. So NH3 was the weak base. NH4 plus was the conjugate acid. So the basic part was NH3, the acidic part was NH4 plus. And they gave us the Kb of ammonia. Now the buffer equation does not change no matter what. But what that means is you need Ka in here, not Kb. So if they gave you Kb, you have to do like what we did in example 8, and you have to find Ka. So remember that Ka times Kb equals Kw. We knew the Kb for NH3. What we were doing is we were figuring out the Ka for NH4 plus. The Ka is for the acid. This is why I added this to the practice questions. Kb It's okay if they give you Kb, but then you have to find Ka to plug it into the buffer equation. And so when you solve for Ka, it's 5.56 times 10 to the negative 10. Because Ka times Kb equals Kw, we assume we're at 25 degrees Celsius. And then it's still the acidic component divided by the basic component. So it's NH4 plus's concentration divided by NH3's concentration. You get an H plus value of 8.89 times 10 to the negative 10. And when you take the negative log, you get a pH of 9.05. So the pH is above 7 because we would consider this a basic buffer. It's a base and it's conjugate acid. So again, the biggest thing with this one is because they gave us Kb, we had to figure out Ka. Had to figure out what Ka was. Now, the last two questions were more conceptual than anything. They did require math, but it was still more conceptual. So I put the question over on the side so that I had space to blow up my answer. So using an acetic acid sodium acetate buffer solution, what ratio of acid to conjugate base will you need to maintain a pH of 5.0? Explain how you'd make a solution. And then I gave the Ka of acetic acid. So I showed both equations just in case, but I used the buffer equation over here. So when you know what you want the pH to be, you know what the H plus should be. So this 10 to the negative fifth, that's figuring out the H plus concentration. So what I started is I started using the buffer equation like we did in example 8. And I said, okay, if I want the pH to be maintained at 5.0, my H plus is going to be 10 to the negative 5.0. Ka of acetic acid they gave us. And so what I did is I divided to solve for the ratio of acid to base. Because the first question it said is what ratio of acid to conjugate base would you need? So when I solved for acid over base, I got 0.556. And so 0.556 is like 0.556 over 1. If I think about it like a proportion on the other side. 0.556 over 1 is like acid over base. So I need 0.556 moles of acid to 1 mole of base. This is the most important part. I know it says explain how to create it, but this is the most important part, is that you would need 0.556 moles of acid and 1 mole of the base. Then if you wanted to create this buffer, if I sent you back into the lab to create this buffer, you would add 0.556 moles of acetic acid and 1 mole of sodium acetate. And then you'd add water, right, dissolve it, make it into a solution. The biggest thing is your moles, right? 0.556 moles of acid, 1 mole of base. So conceptual question with a little bit of math involved with this one. But notice how if they tell us the pH that we want to maintain, and we know what buffer we're going to use, we know the Ka, we can actually figure out what ratio. We can change that ratio to change the pH. And then finally, practice question number 4. So a chemist needs a solution buffer to a pH of 4.3 and can choose from the following list of acids and their salt. So that means that this is the acid, and then we would also have the conjugate base. Calculate the ratio of acid to base required for each system and which system works best. So it looks like I have lots of information here, but here's what I wrote first. If the buffer requires a pH of 4.3, find the acid with a pKa closest to 4.3. If this were a multiple choice question, and I can guarantee you will see at least one multiple choice question like this, almost identical, probably with just different acids. Look at the pKa. So here's the Ka. You can then look at the pKa. And if you look at the pKa of each one of these, whichever one has a pKa closest to 4.3, that's the best acid to use. But since the question said, calculate the ratios, I went through and I calculated the ratios. So just like what we did before. H plus concentration is 10 to the negative 4.3 for each one. Then I had used the Ka values that they gave for each acid. And I divided those to figure out the ratio of acid to base. Now, two things with this. A perfect buffer has equal amounts of acid and base. So the perfect buffer would have as equal of amounts of acid and base as possible. If it's not possible to get equal amounts, then the closest ratio to 1 is going to be the best one to use. Because the closest ratio to 1 means they're close to being equal, and those would have the greatest buffer capacity. It's able to neutralize both acid and base. All right, looking at the particles over on the side, right now I have what, 1, 2, 3, let's do this. I have 3 moles of acetic acid, I have 3 moles of acetate. This would be a very good buffer because it has equal amounts of the acid and of the conjugate base, which means that I can add, in this case, I can add 3 moles of strong acid and the buffer will still work. Or I could add 3 moles of strong base and the buffer would still work. If you don't have very much in your buffer, 1 drop of acid could change. So the perfect buffer has equal amounts. If it can't have equal amounts, the one with the closest ratio to 1 is the best buffer. So the perfect buffer has equal amounts. If it can't have equal amounts, the one with the closest ratio to 1 is the best buffer because it's going to have the highest buffering capacity. So C is the best answer for this question. Another thing that you will probably see on a quiz or test is asking about buffer capacity. Remember, the higher the concentrations, the better the buffer. So the higher the concentrations, the better the buffer. Concentrations of 1 molar is much better than 0.1 molar. So what we're going to do is we're going to build on weak acids and look at buffers, percent ionization. So we're going to be able to review a lot of different concepts that we've looked at before as we're looking at buffers. So at the top, it gives us 2 solutions, and it tells us the composition of these solutions. So here I have HOCl. HOCl, all that I have in this container is a weak acid. I only have a weak acid in this container. In solution 2, I see that I have a weak acid and its conjugate base. So in this container, I have a weak acid and its conjugate base. OCl minus is the conjugate base of HOCl. So number 1 says solution 1 is a 0.025 molar solution of hypochlorous acid. They give us the Ka value. Calculate each of the following quantities for solution 1. So A says the H plus in solution 1, show your work for this calculation. So in solution 1, all that we have in the container is a weak acid. So if it's weak and we need to do any calculations, we're probably going to need an ice table. This is going back to chapter 16 and reviewing chapter 16. So we have a 0.025 molar solution. We have nothing else initially. The only thing in the container is the weak acid. I don't know anything else. So I'm going to use X's. So see if you can plug this into the Ka expression. Solve for the H plus concentration. So I got an H plus concentration of 2.74 times 10 to the negative fifth, because X is H plus. So if that's the H plus, part B says calculate the pH. Well, what do I have to do to calculate the pH? Negative log of that. So take the negative log of 2.74 times 10 to the negative fifth. 4.56. Then part C, the percent ionization of HOCl in solution 1. So now we get to review percent ionization a little bit. So remember that percent ionization is the H plus concentration at equilibrium over the initial concentration of the acid times 100. So we have all of that information already. This is what free response questions look like on the AP test. They build off of parts that we've already solved for. H plus concentration at equilibrium was 2.74 times 10 to the negative fifth. Initial concentration of the acid was 0.025. Multiply by 100. So 2.74 times 10 to the negative fifth divided by the initial concentration of the acid, which was 0.025 molar. We multiply that by 100, going to be a small number. 0.11%. 0.11%. So that's all reviewing from chapter 16. Then if we look at number 2, consider the following equilibrium as you make predictions. So we have the weak acid at equilibrium. It says the major difference between solution 2 and solution 1 is the presence of additional hypochlorite ions in solution 2. Due to the common ion effect, the presence of additional ClO- ions has an effect on the equilibrium shown above. So let's think about this, and then I'm going to have you answer questions A through D. See if you can answer them. We'll go back, we'll check, we can change answers if needed. So now if we have more OCl-, we have more OCl-, now we have too many products. Which way is that going to cause the reaction to shift? Right, left, toward the reactants. So it's going to shift, right? Adding an ion to the products will cause a shift to the left, toward the reactants. So I want you to think about what that would do. If it shifts left, think about what it's doing to the H+, what it's doing to the OCl-, and how that would affect everything. So see if you can answer A through D. So for number 2, if we fill in everything for number 2, we can double check and make sure that you have everything circled correctly. And I'll go through and talk about each one as well. So we talked about part A. Adding extra OCl- ions causes the reaction to shift to the left. So we think about Le Chatelier's principle. Adding an ion causes a shift toward the reactants. So we think about as the reaction shifts toward the reactants, that means that not only is the OCl- being used up, but so is the H+. So the value of H+ is going to be less than solution 1. If you have less H+, if it's less acidic, it's more basic, so the pH is going to go up. And then percent ionization will actually be less than, because percent ionization is H+ at equilibrium over the initial concentration of the acid. So if you have less H+, you have less percent ionization. Any questions on 1 or 2? All right, so if we flip to number 3. Flip to number 3. Now we're focusing just on solution 2. All right, some of these I'll have you do on your own. We'll come back together. So for this, it says in question number 2, you made several predictions. Now we're doing the calculations to verify those predictions. Calculate each of the following for solution 2. Now we said that solution 2 was a weak acid and its conjugate base. If it's a weak acid and its conjugate base, what is it? The buffer. Now you could actually solve part A one of 2 ways. If you recognize that it's a buffer, you can use the buffer equation. If you don't recognize that it's a buffer, you don't recognize it right away, that's okay. Here's the other way that you could solve. You could solve using the common ion. The way that you pick is up to you. I'm going to show the buffer equation because we're talking about buffers. But if you go back and you look at the answer key, you're going to see that I actually solved both ways. You get the same thing. So let's use the buffer equation and let's solve for the H+ concentration in solution 2. Remember the buffer equation is H+ equals Ka times the acid concentration over the base concentration. You would just have to be able to pick which part of the buffer is which. So we already labeled it at the top. So we can plug everything in and solve. We're solving for H+. Ka was actually given to us on the front page. 3 times 10 to the negative 8. And Ka was given to us on the front page. And then acid over base. The acidic part of the buffer is HOCl. That has a concentration of 0.025. The basic part is the OCl minus ion. That's 0.015. You can put it in your calculator and you can solve. So we do 3e negative 8 times the quantity 0.025 divided by 0.015. We get 5.0 times 10 to the negative 8 molar. 5 times 10 to the negative 8 molar. Now if you solved using the common ion, so using an ICE table and having 2 initial values, minus x plus x, use the Ka expression, you get the same thing. You would get the exact same thing using the common ion. So in part B, the pH of solution 2. So we need negative log of H+. Right, that's going to be pH. So take the negative log of what we solved in part A. I got 7.30. And as you go through, check and make sure I've put it in my calculator right. So the pH of solution 1 was 4.56. Once we added a common ion, we created this buffer, the pH went up. So then percent ionization. Again, percent ionization is the H+ at equilibrium. So 5 times 10 to the negative 8. Because what we find in the buffer is also at equilibrium, divided by the initial concentration of the acid times 100. 5e negative 8 divided by 0.025 times 100. I got a tiny number. Even as a percent, it's a very small number. 0.0002%. So adding a common ion, creating a buffer, adding a common ion, lowered the percent ionization. So in number 3, we were just verifying those predictions that we made in number 2. So then number 4, I'm going to read through it, and I want you to look at the 2 solutions and label the 2 solutions and see if you can figure out number 4. Number 4 says, which of the solutions shown above, so you have solution A and solution B, would behave as a better buffer solution? Justify your answer. So you need to either tell me solution A or solution B, but then also it says justify your answer. So what I want you to do is I want you to look at solution A, label what's part of solution A. Look at solution B and label what's part of solution B. And remember that for you to have a buffer, you need an acidic component and you need a basic component. So take a look at each of the solutions and see if you have that acidic component and that basic component. So think about what's HNO3 and what does that mean about NO3 minus? What's HNO2? What does that mean about NO2 minus? So with number 4, hopefully you were able to identify that HNO3 is a strong acid. HNO3 is a strong acid, which means this entire salt is neutral. Na plus is neutral, NO3 minus is neutral. Something to keep in mind is these solubility rules like K plus, NO3 minus, Na plus, those are neutral. NH4 plus is not, that's a little bit unique. But Na plus is neutral, NO3 minus is neutral. HNO2 is a weak acid. Na plus is neutral, which is why we think of it as a spectator. But NO2 minus is a weak conjugate base. So solution A, if we put that into a beaker, all we have is a strong acid. Solution B, we have a weak acid and a weak base. So when we're thinking about which behaves as a better buffer, we should say solution B. Solution B behaves as a better buffer, right? Because it consists of a weak acid and its weak conjugate base. So there is an acidic component and a basic component, right? So it's able to neutralize small amounts of strong acid or strong base. Solution A can't do that. All solution A would be able to do is neutralize base, because all it has is an acid. So solution B is the best because it consists of a weak acid and its weak conjugate base. It's able to resist pH changes because it can neutralize small amounts of strong acid and strong base. So number 5, the value of Ka for HNO2 is 4.5 times 10 to the negative 4th. Part A wants you to calculate the value of pKa. So think about how we did that. All right, think about what that little p means. See if you can calculate the value of pKa. Right, can you calculate the value of pKa? So that little p just means you're taking the negative log. So pKa means you're taking the negative log of the Ka value. It's very common to be required to calculate the pKa. So negative log of 4.5 times 10 to the negative 4th is 3.35. A little trick, when you take the negative log of something, look at the absolute value of the exponent. If this would be 1 times 10 to the negative 4, this would just be 1. Or this would just be 4. you have a number that's in front of the scientific notation that's not a 1, you can actually take the exponent, so the absolute value of the exponent, and subtract 1. So taking the negative log of this number will be somewhere between 3 and 4, which it is. Then part B says make predictions. So we're not doing calculations right now, we're just making predictions about the pH of each of the following solutions. So here's where we're comparing pH to pKa. So I want to review what each of these means. So remember, if pH equals pKa, we have equal amounts of buffer. We have equal amounts of the acid and the basic component of the buffer. If the pH is less than the pKa, the pH is lower than the pKa, think about what it means for the pH to be low. That means we have more of the acidic component of the buffer. And then if pH is greater than pKa, if the pH is high, that means we have more base. So if pH is greater than pKa, that means we have more of the basic component of the buffer. So all we're doing without any calculations is we're comparing the acid to the base. So compare the acidic portion of the buffer to the amount of the basic portion of the buffer. So in this first one, we have 1 molar of the acidic component, 1 molar of the basic component. If they are equal, pH equals pKa. Right, and I'll say because concentration of HNO2 equals concentration of NO2 minus. So here's our weak acid, here's our weak base. Compare the next one, 0.75 molar of the acid, 0.55 molar of the base. So now we have more acid compared to the base. So we're going to say pH is less than pKa because the concentration of HNO2 is greater than the concentration of NO2 minus. More acid means a lower pH. And then we have 0.83 molar acid and 1.1 molar of NO2 minus. That's the basic component. So here we have more base. So we would expect the pH to be higher than the pKa. A higher pH means more base. Right? Because now we have the acid, right, is less than the base, or the base is greater than the acid. So when you have more base, your pH is higher. When you have more acid, your pH is lower. When they're equal, pH equals pKa. We're starting to see more and more questions like this. Multiple choice and free response. Okay, then let's flip to 6. So 6 says in question number 5, you made predictions about the pH values for 3 different solutions. Now it's time to do the calculations to verify that your predictions were correct. Calculate the pH of each solution and then show your work. So see if you guys can go through these. So these are all buffers. So use the buffer equation. H plus equals Ka times the concentration of the acidic component over concentration of the basic component. They gave us Ka on the other page. I'll write it up here so that you have it. 4.5 times 10 to the negative 4th. So see if you guys can go through A, B, and C. See if you can go through A, B, and C. So you're just using the buffer equation 3 times. You're using the buffer equation 3 times. Think about what you solve for out of the buffer equation, though. You're solving for H+, so think about what you have to do with that in order to get pH. All right, so I have those 3 pH calculations up here on the board. So in part A, pH is 3.35, which is what the pKa was. Part B, pH is 3.21, so a little bit less than pKa. And in part C, pH is 3.47, which is a little bit above pKa. So in number 6, this was just using the buffer equation to solve for pH. So remember, out of the buffer equation, you get H+, and then you just take the negative log of H+ to find pH. Any questions on what we've done so far? So we're going to focus on, we'll do 7, 8, and 9 next. And in number 7, it talks about the pH range of a buffer. So the pH range of a buffer is the range in which the buffer acts effectively. So a buffer is not going to work over all pHs. Right? It's really going to work just within a set number of pH units. And so the pH range, and we'll talk about this more when we get to indicators, but a pH range is based on the pKa. So a buffer is usually chosen when the pKa is close to the desired pH of the buffer. So that's why we look at the Ka and the pKa to figure out which would be the best buffer. Buffers that contain equimolar quantities, equal amounts, equimolar means equal moles, usually have a pH range within plus or minus 1 pH unit of the pKa. So pH range, I'm just going to write this over here, is pKa plus or minus 1. So what that means is if we find the pKa of the acid, the buffer works within 1 pH unit down and 1 pH unit up. So the pKa that we calculated before was 3.35. So that means that the pH range for a buffer of HNO2 and NaNO2 would be between a pH of 2.35 and 4.35. So the pH range of this buffer will work between a pH of 2.35 and 4.35. So it's not going to work if you try to have a pH of 10. Right? This buffer is not going to work. That's too much base. You're going to break the buffer. And then 8 and 9 are looking at net ionic equations. So we're going to look at net ionic equations just a little bit more, and then really we just have particle diagrams after this. So a student prepares the buffer solution by combining HNO2 and KNO2. So again, just like sodium, potassium is also a spectator ion. So they tell us this is a buffer solution. So I noticed that this is an acid. It's a weak acid. And here is the conjugate base. Right, the net ionic equation that represents the reaction that best helps to explain why adding a few drops of HCl, which is a strong acid, to the buffer does not significantly change the pH of the buffer solution. So we want net ionic. I'm going to think about the equation. I'm going to think about the equation down here. So if I have a strong acid, that's H plus Cl minus. Strong, it breaks apart. Which part of the buffer is going to neutralize added acid? The acidic part or the basic part? Basic part. Because the point of having both parts of a buffer is so that it can neutralize acid or base. So if we have H plus Cl minus, the basic part of the buffer, NO2 minus, is going to work to neutralize. Neutralize means you add an acid plus a base. Well, think about what a base does. A base accepts a proton. So NO2 minus is going to accept a proton and become HNO2. Right? Cl is not in here. Cl is still floating around in solution. So Cl minus is actually a spectator here. So the net ionic equation is just going to be H plus NO2 minus yields HNO2. HNO2 is a weak acid, which is why it stays together.
I was just wondering, why does the K break off since it's a weak base?
So K plus, so this is a salt, right? KNO2 is a salt because anything with potassium, nitrate, ammonium, or sodium is soluble. And so since this is a soluble salt, it breaks up into K plus and NO2 minus. You technically have K plus floating around in here as well. We just ignore it. So if you did like plus K plus here, and you had plus K plus here, right, that's okay. It's still a spectator. So K plus and Cl minus both cancel. Yeah. And then HNO2 stays together here because it's a weak acid. Right? Only strong acids and strong bases will break apart. So the number 9 wants us to do the same thing, but it wants us to show what happens when NaOH is added. Well, NaOH is a strong base. That breaks up into Na plus and OH minus. We know from the work that we've done so far, Na plus is always a spectator ion. So we're going to have OH minus. Right, because we know Na plus is a spectator, just like K plus is a spectator. OH minus is a base. So to neutralize, the acidic part of the buffer, which is HNO2, is going to react with OH minus. HNO2 stays together in a net ionic equation because it's a weak acid. We know from our work with acids and bases, the acid will donate its proton to the base. And we'll actually get H2O, which is a liquid. And we'll be left with NO2 minus. So notice how when an acid is added to the buffer, like in number 8, the basic component of the buffer works to neutralize. When a strong base is added, the acidic component of the buffer works to neutralize. And they love asking the net ionic equation questions as well. Questions on 7, 8, or 9? So if you flip over to page 10, right, I just want you to read through page 10. Page 10, no, not page 10, number 10. Read through number 10. It gives you buffer X and buffer Y. This, you're going to be thinking about buffer capacity. So number 10 says, which of the buffer solutions shown above will be more resistant? So it tells us that they're both buffers. But it says, which of the buffer solutions will be more resistant to changes in pH when either a strong acid or a strong base is added to the buffer? Justify your answer. So we know that they're both buffers. Look at the concentrations of each. The only thing that differs between them is the concentration. We talked about how the higher the concentration, the more the buffer capacity. So if we answer this question, I'm just going to answer it up here. Right, which will be more resistant? That's buffer X. So buffer X will be more resistant. right? Because it has a higher concentration. So since it has higher concentrations of the acid and the base, you can add more. You can add more strong acid or strong base, and it will continue to work because you have a higher concentration of each. So that's like thinking about having, this example, you have 3 molar of each. Well, what if I change the concentration to only having 1 molar of each? Well, now I can only add 1 acid or 1 base for this buffer to work. The more I add, the higher the concentrations within the buffer, the more it can neutralize. So that's looking at number 10. Number 11, we're going to skip for now. So we're going to skip number 11 because that's a titration question. And then we have number 12. So number 12 says use the information in the table above to calculate the pH for each of the following solutions. So you're calculating the pH of all of these buffers. So use the buffer equation, more practice with the buffer equation. So I'm going to have you guys do these 3 questions. Right? Calculate the pH of each of these. And they give you all of the Ka values, so you don't even have to do any conversions from Kb to Ka. Right, so use the information in the table, calculate the pH, use the buffer equation. Buffer equation is just H plus concentration equals Ka times the acidic component of the buffer over the basic component of the buffer. So use that for all 3. You just need to make sure that you can figure out which one is the acid, which one is the base. And each and every one of these are buffers because it's an acid and its conjugate base or a base and its conjugate acid. You just have to figure out which part is which. I know part B looks a little weird because they both have sodium, but just ignore the sodium. All right, remember that the acid always has 1 more H plus. When you're thinking about what goes on the top, you're looking at the one that always has 1 more H plus. So if you take a look, I know I didn't show the work over here. And all of these are actually equal amounts, right? 1 molar of each. So for all of these, the acid equals the base. So technically, since they all have equal amounts of acid and base, that actually means that the pH equals the pKa. So for each one of these, because they had equal amounts of the acidic component and the basic component, pH equaled pKa. All right, so the very last question. This is looking at particle diagrams, and this will probably go fairly quickly. For this, up at the top, it says hydrofluoric acid, HF, is a weak acid with a Ka of 6.8 times 10 to the negative 4th and a pKa of 3.17. So they are already giving us the Ka and the pKa. So they already did that negative log calculation for us. It says 3 different buffer solutions are prepared that contain mixtures of HF and NaF. So they're telling us we already have 3 buffer solutions. A particulate representation of a small representative portion of each buffer is shown in the table below. Cations and water molecules are not shown. So they're not showing Na+ because that's a spectator ion, and they're not showing water because it's water. And it says make predictions about each about the pH of each of these buffer solutions. So here's the first thing that I'm going to say. When you have particle diagrams, count. Particle diagrams are nothing more than counting. Okay, so here's our 3 buffers. All right, it gave us the key at the top, and we're making predictions about how pH compares to pKa. So it gives us this 3.17, but remember that's the pKa. So we're looking at, do we have more acid, more base, or are they equal? Count them. Count your HF and count your F minus. So if I look at buffer 1, 2, 3, 4, 6, 7, I have 8 molecules of HF. And I have 1, 2, 3, 4. I have 4 molecules of F minus. So if we have more acid, how should our pH compare to our pKa? If we have more acid, the pH should be less than the pKa. And I'll just make a note here. There is more acid than conjugate base. All right, so pH will be lower. Could you do a calculation? Yeah, sure, you could. But you don't have to. You're just comparing acid to base. So do that for questions 2 and 3. Count how many HF, count how many F minus, and think about what that means in terms of pH and pKa. So for question 13, again, particle diagrams is all about counting. In buffer number 2, you had equal amounts. Equal amounts means that pH equals pKa because H plus equals Ka. And then in number 3, you have more F minus than HF. F minus is the base. So if you have more of the basic component of the buffer, pH is greater than pKa.